So let's look at the second question here. It says, consider a strain gauge with sensitivity of 2 to be in the quarter arm in R2 position of a Wheatstone bridge, where R3 is equal to R2. So we are asked to derive an exact equation. Right. So this is the Wheatstone bridge here. This is the input voltage, and this is the output voltage, which is BD. We want to determine the voltage between point B and D. So this is the equation determining the voltage between point B and D. And then considering null output, it means our initial setting will make it to be 0. Considering null output, it means E is equal to what? 0. So when you equate E equal to 0, you will end up having R3 all over R3 plus R4 is equal to R2 all over R2 plus R1. And I'm sure in this case it will give you, when you resolve, R1, give you R1, R3 is equal to R2, R4. Remember, we are given that R3 is equal to R4. So if R3 is equal to R4, implies also that R1 is equal to what? R2. Already we are given that R3 is equal to R4. Remember, the strain gauge is placed at point 2. So it's the only one that is going to change. The others are not going to change. So considering there is change in gauge resistance R2, remember the final is going to be now change in voltage. The output voltage is going to be final minus initial. This is the final, and so you will add R2 because it's the one that is reacting to change in resistance. And then when you substitute R1 is equal to R2 and R3 is equal to R4, this will reduce to 0, and you will have the equation to be this finally. Okay, so when you're able to have this, then you substitute, you introduce R2 and R2 up and down, right? Then you can have it this way, and then you can substitute your SA. Remember, change in R2 all over R2 is equal to what? SAE. And so when you substitute it correctly, you will end up with minus 4E all over 4 bracket 1 plus 2E. But remember also that 1 over 4 R1 R2 all over R1 plus R2 all squared. When you do it together, R1 is the same thing as R2, and so it's the same thing as R1 squared all over 2 R2 what? Squared. And so this is going to give us 1 all over 4. And so we can substitute 1 over 4 with SAE, and finally we will have everything is equal to 4R minus 4RE all over 1 plus 2E. And then we bring the R down. Remember, R, 1 over 4 is equal to what? R. So you substitute 1 over 4 to 1/4 to replace R. And finally, we can have it this way. Minus 4E all over 1 plus 2E. So this is our final equation. This is the exact equation, because in this equation you can see we have strain. It's not linearized. This is the exact actual what? Equation. Here we're asked to determine the exact equation. So you can see from the question it says, using equation x and y, derive the exact equation. This is the exact equation we have determined, right? And this equation is given by, this is the exact equation, because this one is not an approximation or is not a linearized equation. So we call this exact. Here, what I'm trying to say that the equation is non-linear, so it's proportional but not linearly, right? Because you have also strain here at the denominator, so it is not a directly proportional relationship. So it's a non-linear equation. You can see what we are having here is minus 4 strain over 1 plus 2 strain, right? The normal strain is what? Is non-linear. So this is the exact equation. Then next we look at the linearized equation, because from the question here, we are asked to what? Plot, this is the exact equation, plot the exact equation we are able to prove, or we are able to come up with. We should plot it as a function of the strain value from 0 to, in between 0 to 0.1. Also here we are asked to plot linearized equation. So since we have found the exact, so let's determine the linearized equation so that we can plot them side by side, and then we can be able to see the difference. So for this, the linearized equation, already we know this is the linearized what? Equation for the Wheatstone Bridge, where here we have all the arms have an active what? Active resistance. It means the resistance, the arms of the resistances or the resistors, we expect that there is going to be change. But in this case, our strain gauge is only placed at what position? At R2 position, right? So since is at R2 position, then it means here only R2 will what? Will react. All the other changes will be what? 0. So it means all this will be what? 0. And this will also be what? 0. So in this case, we are going to end up with change in E all over, change in output voltage over initial voltage divided by a constant R is equal to what? Minus change in R2 all over what? R2. And this is the same thing as what? Change in R2 over R2, remember, is equal to SE. Right? The sensitivity is equal to SA. Change in R2 over R2 is equal to SA multiplied by the strain. So we can see that this equation now, change in output voltage all over the input voltage divided by a constant is equal to what? Minus SAE. So let's compare these two equations. These are the two equations we are expected to plot. This is what we call the approximate or linearized. Linearized. Remember, for the linearized, we make approximations, right? Or we call it approximate what? Equation. In this case, we are able to make this exact equation to be what? To be linear. All right, so let's see the plot. Let's see the error. So the next part of the question says, what? Tabulate the two equations in increment of 0.01 by giving the percentage error in each of the equations. So we are going to compare the two equations. This is it here. We plot it in, you can plot it in Excel or on a graph sheet. So from 0, the strain values, we are expected to use strain values from 0 to 0.1 with an increment of 0.01. So here, this is the exact equation, but because they are negative, this will also be negative. If you look at it, what we derive, the exact equation we derive, because it is in the R2 position of the Wheatstone Bridge, in this case, it's giving us negative, right? Even the exact equation. And since also the linearized, also we can see that it's also what? Negative. Assuming it is in the R1 position, the exact is going to be what? Positive. And also the approximate or linearized is also going to be positive. So now let's plot these two and see the difference. So here it is. This is the exact. Both they are negative, so we'll have a negative slope, right? So this is the approximate. And then we are expected to determine the percentage error here in this case of the, where do we have error? It means we have error in the approximate, isn't it? So we are going to determine the percentage error with respect to the approximate, which is equal to the error, which is linearized, minus exact all over what? Linearized. So we want to see the error in the linearized multiplied by 100. So each of these values of the equations, you determine the what percentage error. So the first one here is minus 0.0392. You can see it's close to what? Minus 0.04. So minus 0.04 is the approximate. Right? Remember, the approximate is just strain value, the sensitivity multiplied by the strain value. In this case, it's going to be 0.01 multiplied by SA, which is 4. Right? But remember, because we have negative in the equation, we also use the negative symbols. Right? So here is 2. Yeah, the next one here at a strain value of 0.2 is 4. So if you do it correctly, the question says, for what value of the strain is the error of the linear equation less than 5%? So here for 0.01 we have 2%, for 0.02 we have 4%, for 0.03 we have 6%. So it's going to be in between 0.02 and 0.03. So invariably, I'm sure when you do it, strain value of 0.025, if you do it correctly, the percentage error, which is going to be, though we don't have the value here, right? We didn't compute it for 0.025, but if you do it correctly, you will end up with 5% percentage error. So it means, for what value of the strain is the error of the linear equation less than 5%? You know, the error basically is on the linear equation. So it means it is for strain values less than 0.025. Anything greater than 0.025, the error is greater than 5%. If it is 0.03, the error is what? 6%. So it means you can even see from here, from the two curves, almost you can't even differentiate between the two lines because the error is very small. It is at higher strain values that the error is what? Is clear, right? The error is becoming clearer the higher the values of what? The strain value. So at smaller strain values, thus at 0.025, the error is less than what? 5%. Yes, so this is the last part of this. So let's look at the next question. The next question says that show that the linearized change in output voltage of a simple potentiometric circuit with one of the resistors serving as a strain gauge is given by change in E equal to, this is also similar, change in output voltage, which is equal to what? Input voltage multiplied by the strain values at maximum circuit what? Sensitivity. And gauge sensitivity SA equal to what? 4. When you are giving gauge sensitivity, it means the strain gauge what? Sensitivity. So let's look at this question. We are asked to prove what? This for a potentiometric circuit given this, and also at maximum circuit sensitivity. So at maximum circuit sensitivity, normally we said R1 is equal to what? R2. So this is the diagram of the potentiometric circuit, right? So this is the other resistor, and this is the where we place our what? Strain gauge at the R2 here. Are we following, please? This is where we place our strain gauge. So it means we are going to also be looking at, it means where our strain gauge is changing, the resistor that is changing is what we are going to be measuring the output, isn't it? Please don't confuse, because in the initial one we use the output voltage to be what? In this case, our output voltage is E. But in the previous question, our output voltage is what? Is capital E. In this case, in this question, our initial voltage is what? Our input voltage is E0. While from the previous one, our input voltage is what? Is V. Right? As we can see from this diagram, input voltage and output voltage. So it doesn't matter. You can use any symbol, right? So it means we have to measure our output voltage because this is where the strain gauge is going to react, right? After being loaded, when you load the strain gauge, any type of loading, whether tensile, tension loading, or compression, or torsion, the strain gauge is going to also experience the loading effect. But in this case, the loading effect is going to be transmitted in terms of change in resistance. because we can't measure the strain directly. So after it has, imitated the loading effect on the actual component or on the specimen, it means the strain gauge resistance will change. But we cannot be able to determine the strain directly. But as I said earlier, we use the principle that change in strain, change in resistance over initial resistance is proportional to what? To strain, where we have a sensitivity. So it's like the strain gauge is like a transducer. It doesn't measure strain directly, but then you use like a converter, convert from one quantity to another quantity. So in actual sense, when you use the strain gauge for a variety of loadings, what you are going to get is change in resistance of the strain gauge, which will then convert that change in resistance to what? Strain. After the loading, you pick the strain gauge and come and place it in either potentiometric circuit or Wheatstone Bridge circuit to be able to determine the output voltage from where you can be able to determine the what? Strain. And R is what? Is the circuit sensitivity. While SA here is the strain gauge what? Sensitivity. So there are two sensitivities in this case when you are using the Wheatstone Bridge or the potentiometric. So in this case, next is we determine the equation, determine the output voltage, which is final. This is the final voltage because it's going to change due to the output voltage, right? As you place your strain gauge here, it will, react. Already we know the initial strain gauge, which is R2. And then the final is going to be what? R2 plus change in R2. And this is going to be the same. This is the initial, and this is the final. And then you come here, simplify your equation. Here is going to be change in R2, and here is going to be change in R2, R1. So in this case here, we are coming up with this when you simplify, but because this is where we are going to do the linearization, right? Because you can see the change in output voltage over the input voltage is what? Is non-linear. Right. So to linearize it, we make some assumptions. So if R2 is much, much higher, then we can be able to neglect this component. If R2 is a bit bigger, we can neglect this component to be what? To be 0, right? And so we'll end up with this particular equation. Then we can multiply through by what? By R2. So when we multiply through by R2, up and down, then we are going to have R1, R2. So this is the first R2 I'm multiplying all over R1 plus R2 all squared. So the second R2 at the denominator here is changing R2 all over R2. Remember, changing R2 all over R2 is the same thing as what? Sensitivity multiplied by the strain value. So we'll have it this way. This is circuit sensitivity. This component is we call that circuit sensitivity. That's the potentiometric circuit sensitivity. And this is called what? SAE. Because changing R2 over R2 is the same thing as what? The sensitivity of the strain gauge multiplied by the strain value. Remember, this component, we call it what? Circuit sensitivity. You can give it K. So at maximum circuit sensitivity, R1 is equal to R2. And this implies that this sensitivity becomes, when you resolve it, it's going to be R2 1 squared all over R1 squared 2 what? R1 squared. So 2 squared also is what? Is 1 over, is 2 squared is 4, isn't it? And so this will cancel and it will give us 1 all over 4. And here our equation will be changing what? Output voltage all over input voltage is equal to, when you substitute appropriately, you substitute the circuit sensitivity, which is 1 all over 4, and then multiply by SAE. Remember, our sensitivity we are given is what? 4. So it's going to be here 1 all over 4 multiplied by 4E. And the 4 cancels. So in this case, change in E is equal to input voltage multiplied by E. So here we have proved it. Are we following, class? Are we following? We look at the next question. So the PDF question, we have solved this. You know, this one here, we solved one of it. The one we solved yesterday was for the delta, right? You can also solve for the what? For the rectangular rosette. That's the 90 degrees, you know, interval. 3-element rosette, strain gauge rosette intervals. So next here is this question. We just solved it. We just finished it today. This is similar to what we just solved earlier. Similar, this question 8.21 is similar to what we just solved, but the only difference here is that the strain gauge is placed at R1 arm of the Wheatstone Bridge. So in this case, our exact equation is going to be positive, right? And also our linearized is also going to be what? Positive. The next question says what? A single strain gauge in a quarter bridge circuit is mounted on the outer surface of a solid circular shaft of diameter D, which is loaded by torsional moment T. So the question here asks us we should show the orientation of the gauge, which will provide the maximum tensile strain on the gauge. What is the strain output of the gauge in terms of TD and the shaft material properties? The shaft material properties are the Young modulus and the Poisson ratio. So there are two things here we are asked. Show orientation of the gauge, right? How this measurement is going to be done on the shaft loaded by torsion. And secondly, we should determine the strain what is the strain output. So this is it here. When you have a shaft loaded by torsion, torsional loading, then how do we arrange our gauge? So this is the arrangement here. When you have a shaft under torsion, this is how you are going to arrange it. 45 degrees along the axis, right? Can you see? So the gauge is going to be arranged. This is the first part of the question. This is torsional what? Strain. So for you to have the strain here is going to actually is going to measure what? The strain gauge actually is going to measure what? Strain, but in this case, this arrangement, when you have torsion, what do you expect? Are you going to have normal strains or shear strain? We're expected to have shear strains and shear stresses. But then the arrangement of the gauge, show the orientation of the gauge. In this case, we only have single gauge. So the orientation is going to be, either you can orient it this way, which is at 45, right? From the axis, which is 45 degrees from the axis. Let me make it in a bigger picture. So it's going to be something like this. From the axis of the what? Of the shaft. So you load your strain gauge like this. Assuming this is the strain gauge. So this is the strain gauge. So it will be loaded what? 45 degrees. Because this is what? This is the orientation that will provide the maximum what? Strain. I think we also have it in our notes. This is part of it here. When you can see torsional loading. So you arrange it from the axis, should be what? 45 degrees. So next, the question asks us the next question is to determine what is the strain output of the gauge in terms of TD and shaft material property. So let's look at that. So if it's placed as one of the arms, it means all the other arms, the change in all the other arms will be inactive, isn't it? There won't be change in resistance. It means the other arms will have constant resistors. So since they have constant resistors, it means there will be what? 0. Are we following? So these all other arms will be? Yes, 0. So I will end up at maximum circuit sensitivity. You know circuit sensitivity, which is this. This is our circuit sensitivity. That's in this case, the circuit is what? Is Wheatstone Bridge. So at maximum circuit sensitivity, R1 is equal to what? R2 implies circuit sensitivity K is equal to 1/4, which you can also prove it, isn't it? So it's going to be 1 all over 4 multiplied by, so it is left with change in R1 all over R1. So in this case, our change in R1 over R1 is same thing as what? SAE, right? SA what? EO, we say E1, it doesn't matter. SAE1, where E1 is equal to what? A. But remember, because it is torsional loading, we will have to relate this with what? With torsional strain. This is a normal strain, right? But then we have to relate it to torsion. So remember the equation for what? For shear, when it is tilted at 45 degrees, we are going to have E1 is equal to what? Because we only have one strain gauge here. So it's going to be E1 equal to, you know, the formula is going to be EA. So in this case, EA is equal to E1 is equal to what? EX plus EX by 2. In this case, it's at 45 degrees. Theta is at 45 degrees over 2 plus what? Plus EX minus EY all over 2. It's going to be cos 2 theta, which is cos 90 degrees. And then plus shear strain all over 2 sine 90 what? Degrees. Sine 2 theta, sine 90 degrees. Are we following? Cos 90 is what? Is 0. And sine 90 is what? 1. So we'll end up with this equation. So this is the only equation we are going to have, right? If we apply the, if we determine the, if we want to determine the complex what? Strains. So in this case, remember that EX and EY, do we have normal strains here? Because it's torsional, it's torsion, the loading is torsion, so EX equal to 0 and EY equal to what? 0, because these are normal strains. So for torsion, we don't have what? Normal strains, right? For pure torsion. So in this case, we end up with E1 is equal to what? The shear strain divided by 2. So invariably, we end up with E1 is equal to what? Shear strain divided by what? 2. So we can make E1 the subject of the formula here, E. So in this case, E is equal to what? The shear strain divided by 2, which is equal to what? So make E the subject of the formula is going to be change in output voltage over input voltage multiplied by 4 all over circuit sensitivity. Remember the question asks us to determine the strain value in terms of what? TD and EV, material property. So now strain is equal to what? That the strain, right? The strain output from the Wheatstone Bridge is equal to what? Half of the shear strain, right? Because the loading is torsional loading. And so we'll have to relate, in that case, we expect that we are not going to have a normal strain, we are going to have shear strain. So we have to relate. From here, normal strain is equal to what? Half of the shear strain. Remember, shear strain is equal to what? Shear stress all over material property, which is shear modulus. Right? From this equation, this is an established equation. Sorry, shear stress over shear strain is equal to what? Shear modulus. I think this is established, isn't it? And so the shear strain is equal to, in this case, the shear strain is equal to tau all over G. Then you have this 2 there. Are we following? And then we also know this the formula is established. In 300 level, we have done this. Maximum shear stress is equal to what? 16 multiplied by torque all over pi d cubed. This is the maximum what? Shear stress. Remember, we have also G2 what? G here. And then finally, we can substitute. So from here, we can see that we have our torque and D. Because the question says in terms of what? TD, the strain output in terms of TD, E, and other material properties. So here, in this case, we don't have Young modulus. So there's a relationship between Young modulus and shear modulus. So we use that, and at the end of the day, the normal strain, so we are going to have the normal strain is equal to half of the shear strain, which is equal to what? 16T. So when we substitute the shear modulus, the 2 will come up, 2 times 16 T bracket 1 plus mu all over 2 E so when you simplify, 2 cancel 2, so we have this is finally equal to 16 T. T is the torque multiplied by 1 plus Poisson ratio multiplied by torque all over pi d cubed. So this is our final what? Equation. Remember, this is the maximum strain value, but the strain value actually doesn't give us a normal strain. It gives us a shear what? Strain. But the question, so this is the actual equation. So the next question asks us to determine, okay, here in this case is similar to what we just solved now, but the difference here is, in this case, we are using a 2-element rectangular what? Strain gauge rosette. It's mounted on the outer surface of a circular shaft. Here we're also using a shaft which is loaded by torsional moment. So show the orientation of the gauge, which will provide maximum tensile and compressive strain on the gauges. If the tensile gauge and compressive gauges are connected to adjacent arms of a half-bridge circuit, what is the output strain in terms of TD and EV? Yes. So in this case, this loading now where is clear. The first one is on one of the arm. In this case, the 90 degrees. In this case, we are having this. Right? So how do this? We are expected that it's going to be placed under torsional what? Loading. So torsional loading, it is going to be, for us to have angle of twist, is going to be in the opposite. Right? So how do you arrange this? A 2-element rectangular. When you say rectangular, you know it's 90 degrees, isn't it?
Yes, sir.
So we can convert this 90 degrees to shear, because this is a shear, this is a torsional loading, right? So since we are having torsion, we can, for torsional loading, we can make this shear in the sense that when we have it this way, here is going to be 45. So it means we can treat it this way. Can you see? Here is 45. Here is 45. So we can convert 2-element rectangular rosette to what? To a shear. So if you convert it to a shear, it means you are going to place it this way, because in this way it can be able to measure what? Shear strain. So in this case, you have to apply it this way. So that here is going to be what? 45. And here is going to be what? 45 degrees. So in this case, our 90 degrees, our rectangular rosette 2-element is converted to what? A shear 2 what? Element. And this is the configuration also here. Can you see? So in this case, you have to place it, because this is torsional loading. But if it is something like this is axial loading, then you can place this perpendicular, just as we have it in the note here. So in this case, if this one is EA and this one is E what? B, then we are going to have EA minus EB is equal to what? Shear strain. I don't want to prove it again, right? Yes. And remember that EX and EY are not even 0, right? Because there are no normal strains in a torsional loading. So we'll have only, because this is a pure torsion, we are going to have what? Shear strain. I've proved this earlier, so I'm not going to prove it now. It's similar to this part also. When you redo it, the other one, in this case, we are only having EA. When you have EB, when you do the two equations, they will cancel out. So it's similar to what we just did now. So in this case, we'll end up with a circuit sensitivity. Let's look at the circuit. It's going to be is going to be changing E all over E is equal to what? The circuit sensitivity at maximum circuit sensitivity is going to be 1 over 4. And in this case, we are going to have an SAE can factorize out. So it's going to be E1 minus E2. The tensile and what? Compressive. So we can make it the subject of the formula E1 minus E2. Remember, E1 minus E2 in this case is going to be equal to what? The shear strain. You know, because it's in torsional loading, which is equal to what? Change in E all over E multiplied by 4 SAE. But we're asked to find determine our output in terms of what? This component. T tog, diameter, Young modulus, and Poisson ratio. So it's the same scenario we just solved now. So all you need to do is, in this case, there's not going to be any 2, right? In this case, the shear stress is divided by 2, isn't it? Hello? For the previous question, the shear strain is divided by what? 2. But in this case, it's not going to be divided by 2. So you convert the shear strain directly, which is going to be equal to what? Tau all over G, which shear modulus, which is going to be equal to 16 all over 2G. Because here we see, because we have 2 arrangement of the strain gauges. Okay. Yes, since we have 2 arrangement of the strain gauges, and if you prove the equation correctly, let me go back to the equation. This is it here. We have 2 arrangement of the strain gauges, and you can see when you have 2 arrangement at 45 degrees, what are we going to have? Only the shear strain. You know, because it's in torsion, so we have to relate it with what? Shear strain. So that's why I say I'm not going to prove this again. We substitute, and finally, when we substitute G, the shear modulus, our equation becomes, and so our resultant tensile and compressive strains to 32 after substituting the shear modulus 1 plus is going to be equal to all over pi d cube. Remember that this arrangement also has temperature compensation, whereby if there is error due to temperature from the tensile gauge, let's assume it's going to be due to temperature, increase due to temperature from the tensile 1 is going to cancel with, it's going to be neutralized with that from the effect of the compressive. So the temperature compensation as the effect of the error due to temperature will cancel out to become equal to 0. So last, the question we have here is a 2-element shear strain gauge is shown below, where the three terminal tabs 1 to 3 can be connected to the bridge circuit. So indicate which position of the bridge the gauge terminals 1, 2, and 3 should be connected such that the output of the circuit is directly related to the shear strain only. So this is the sketch of the circuit. So what connection will make so that the output of the circuit will measure only the shear strain only. So in this case, it means we should make the connection in such a way that these 2 strain gauges 1 and 2 should be able to measure 2 of the arms. So in this case, the only way we can have this is we have several combinations. These are the combinations. So in such a way that for us to measure shear, we need, for example, first one, it should be placed at E1 minus E2, because E1 minus E2 from this equation will give us difference, because this is a shear strain gauge, is a shear 2-element shear rosette. Whenever you have 2 of the gauges subtracting each other's, then it will measure what? Shear. So if you have E1 minus E2, it means the strain gauge 1, 2 should be connected. 2 should be connected, for example, when we say E1, E2, then 2 should be connected at 2 should be at B or equal to B, and then 1 should be connected to C, 1 should be connected to C, and then 3 should be connected to A. So we can also have another format here. We can also have another difference, which is we can have E1 minus E4. So if this is the arrangement, it means in each of the case, the shear strain must occupy a half bridge, right? It should cover 2 of the arms. So in this case, when we have E1 minus E4, it means 2 should be connected to A, 1 should be connected to B, and 3 here, 3 positions should be connected to D. In this case, we'll have a difference, and that difference will give us the shear strain. As we have proved earlier, that the shear strain is equal to difference in the values of the strain gauges. So we can also have another scenario, E3 minus E2. And so if you have this scenario, then it means 2 should be connected to C, 1 should be connected to D, and 3 should be connected to B. And we can also have the last scenario. If you look at the equation here, the right hand side, we can also have E3 minus E4, right? So we can have E3 minus E4. So if you have this scenario, it means 2 should be connected to D, should be placed at D, 1 should be placed at A, it means point 1 should be placed at A, and point 3 should be placed at C. So these are the various combinations we can have. So each one of the combination you make, you write, you express, is the answer. So the second part of the question, the last part of our question for today, for these tutorials, says that considering that the output of the bridge gives a direct reading of the strain, if a single strain gauge is connected across terminal AB. So determine the output of the circuit if the arrangement of the shear gauge, as you have indicated in A, is employed. So what is the output of the circuit? The output of the circuit is actually a shear strain. So this is the A part. This is the A part. So the output of the circuit, it means you are going to prove that equation for the shear. So I've proved it earlier. So the proving is the proving is actually this A. Assume one of the strain gauge is A, the other one is B, then we have EA minus EB is equal to what? EXY. So this is the proving I expected to determine. In this case, when we use this, it means it's going to be in this form. Here, assume here is EA, and here is EB. You know, this is for trial. So this is tilted, you know, the other way around. So this is it. Assuming here is EA, and here is EB. So when you do, you can turn it down. So when you tilt it 90 degrees, you can have it in this way. So when you compute it correctly, we can only determine one of the complex strain. We can only determine one of the complex strain, which is the shear strain. We don't even need because this will not even provide result for the normal strings EX, EY, because it's only. So we have come to the end of our tutorials. I hope you enjoyed watching my videos. Thank you.